My name is Peter. I'm a PhD student with another Peter at Berkeley. And I work on deep reinforcement learning. So in this lecture, we're going to talk about derivative-free optimization and evolutionary methods. And as you will see, it's really just a special case of what John has mentioned in the last lecture. So we have basically seen many methods to optimize an agent. And we have value-based methods, we have policy gradient-based methods to optimize it. And most of those methods exploit a lot of the problem structure in the sense that you execute an action and you receive next state and reward, and you repeat these cycles. And dynamic programming is the most common kind of methods that exploit those structures a lot. So in value-based methods like value iteration, Q-learning, you write down the Bellman equation that describes the consistency constraints of the optimal solution. So there you actually exploit a lot of the problem structure of the MDP, and that usually gives you very efficient sample usage when you do make them to work. And from many of the recent lectures, we have also seen another branch of techniques called policy optimization. That is, we have some policy that's parameterized by theta, and then we directly write down an objective function. That is the expected return that we would get if we execute this policy, which we can call U of theta. And in policy optimization, what we would try to do is we directly change parameter theta in a way such that it would increase the performance of our policy. And we have already seen policy gradient methods, and some special cases of them include actor critic methods where you also learn a value function or critic to also exploit the problem structure a little bit, which is like a hybrid between policy optimization and dynamic programming. What we're going to talk about now is also falls under policy optimization, which means you also have some parameterized policy that you try to change directly to improve your performance instead of estimating some kind of values. But the difference between evolution or derivative-free optimization is that you wouldn't try to exploit any problem structure. So for the purpose of this kind of algorithm, you can even forget that you are optimizing an MDP. It could be any black box function. So evolutionary methods, how does it work? We have some objective function that we try to optimize. And then the general algorithm goes like following. So you have some parameter theta, and then you make some random changes to the parameter theta. And if the result improves, you would keep the good changes. And you just repeat. And that's basically the whole algorithm. Would you be happy if I call it done now? So let's see, like a more specific example of that. A very popular choice of evolution algorithm is called cross-entropy. So what it means is that when you randomly perturb your parameter, you perturb it by some diagonal Gaussian distribution, so which we can parameterize by some mean vector and standard deviation vector. And each iteration, what you would do is you would sample n random parameters from this Gaussian distribution. For each parameter, you get one policy. And you just roll out that policy, get some trajectory tau I, and then get its return. And after you have collected all those trajectories, you will simply select the best k of them, ranked by the return that they have got. And k usually is something like 10% to 20%. So you basically throw away the worst 80% and then keep the best 20%. And then for those parameters, you fit another diagonal Gaussian to it. Do maximum likelihood. And then you update your mean and standard deviation. And that's the whole algorithm. You just repeat until the performance satisfies you. Is that clear? OK. It works really well, like almost embarrassingly well. So in the approximate Q-learning lecture, we talk about like the state space of Tetris and how it actually has a huge state space because of the combinatorial structure of the problem. And it turns out with some relatively simple policy class, you can do really well with just this type of simple method. you can find really, really good performance on this Tetris game. And what's even more embarrassing is that for all of those value-based methods that try to exploit clever dynamic programming properties, it actually took them another 7 years to catch up the performance. So the first paper that was using cross-entropy to optimize a policy for Tetris was published in 2006. And then the approximate dynamic programming method only caught up in 2013. So yeah, sometimes it works, like this kind of brute force approach works even better than the clever approach that try to exploit problem structure. So just want to point out, for this kind of policy, usually it's some low-dimensional policy. So specifically in this example, the policy only has 22 free parameters. So it's a relatively small parameter setting, which is why you would kind of expect, okay, yeah, because the parameter dimensionality is so small, I can just make some random changes, and sometimes I would find some good parameter, and I can make progress there. It actually works on even slightly higher dimensional problem. So this type of method has been pretty common in graphics community to optimize their controller. Yeah, so this is like a humanoid type of robot. They have about 30 degrees of freedom. And then they are learning a control policy that will be robust against external perturbation. So the yellow arrow is the external perturbation that you apply to it. And you can learn quite robust working gate. And this type of policy is slightly more complex. So it has roughly 100 free parameters to tune. It has so by contrast, a lot of the like humanoid policy that you have seen yesterday have on the order of 100K parameters as opposed to 100. So the difference is that in graphics community, you usually have pretty hand-engineered policy class that exploit a lot of the morphology of the object that you're trying to control. But then the question is, if we want to learn a deep networks that take raw sensory input and make no assumption about the object that you're trying to control, can you still use this type of evolutionary methods? So that's the next question that we would look into. So basically, we have seen very simple type of methods, just do random perturbation and keep the best 20% and just repeat, could do really well on optimizing those kind of low-dimensional control problem. But can we make them work with deep networks that have 100,000s or even millions of parameters? So before we do that, we would like to give you a different light on evolutionary method instead of like just looking at it as randomly sampling and then keeping the best K%. So precisely, we can look at the problem as learning a distribution of processor parameters. So say if we have, say we have a parameter theta that's drawn from some parameter distribution. That itself is parameterized by mu. Let's say the mean of Gaussian. Then the goal of the problem is we want to maximize the expected return if we randomly sample one policy from that parameter distribution. So first we will sample some random parameter. First we'll sample a specific parameter from that parameter distribution, and then we will roll out that policy in the environment. And then we would measure the expected return from that specific policy. And this is the objective that we are trying to optimize. So you should be very familiar with this now. With this form of problem, you can easily get the gradient of it and perform gradient ascent by likelihood ratio estimator or policy gradient. So basically, you can rewrite this problem into the following form using the log likelihood trick. But what's different from yesterday's policy gradient lecture is that right now we are not taking the grad log of action. Right now we are taking the grad log of parameter setting with respect to mu, the mean of the parameter distribution. So the first thing to realize is that this type of gradient estimates ignores a lot of information. Like, look at the whole equation. there are no states in it, there are no actions in it, and there are no rewards. All of those things are being discarded. And if you look at the whole gradient estimator, the only thing that you need is storing data and then storing the return that a specific data gets. So those are the only two things that you store as opposed to the whole trajectories. So this would turn out to enable very scalable distributed training methods. We will see more of this later. So let's just work out a concrete example of like what this type of gradient estimate would look like. So suppose, again, our parameter theta is just a diagonal Gaussian distribution with some mean mu that we want to tune, and then we assume we have some fixed covariance matrix. So if we write down the log density of this distribution for any given parameter theta, it looks like the negative quadratic of mu from of theta from mu divided by 2 sigma squared plus some constant term that doesn't matter because we are going to take a derivative with respect to mu. So if we do that, it ends up with the following simple form. And say now I draw 2 samples from my Gaussian distribution, theta 1 and theta 2. And from this, we can obtain 2 trajectories, tau 1 and tau 2. And the sample estimates of our distribution would look like the following. It would essentially be grad log p of theta 1, which is in above, times the return that you get from tau 1, plus grad log p of theta 2 times the return from tau 2. So basically, you can see if our parameter theta, suppose our parameter theta 1 is good, and we get a positive return from it. And suppose our parameter theta 2 is bad, and we get a negative return from it. Then what this equation and what this gradient is doing is precisely telling the parameter to move towards theta 1 and move away from theta 2. So this is precisely the evolutionary methods, the philosophy of evolutionary methods. We try some random things, and then we move, and then we keep the positive changes. But instead of like doing it in the non-parametric way, what's happening here is you're keeping the good changes in a smooth and parametric way. Any questions so far? Yes. Yeah. So if you have a good range, it usually works quite well. Yeah. That I'm not so sure, but I mean the problem with tuning hyperparameters is that because like just pure random search already works really well. So you just like give it some like log range and then just do uniform sampling. It usually already works. So like this might work marginally better, but I don't know. Okay. So one interesting connection that we will see from here is that this type of method of learning a distribution of parameters is actually very closely related to finite difference. And we would spell out the connection here. So one trick that you can use to reduce the variance of this type of gradient estimate is called antithetic sampling. What it means is that instead of sampling a bunch of points and then evaluating those points, you will sample one point with some noise vector and then sample the mirror of that. So this is precisely what I mean. If you have a, because our data is drawn from a normal distribution, it could be rewritten as a mean plus some standard normal noise times the scaling, the standard deviation sigma. So basically, that means if we have some random normal noise epsilon, then we can draw one sample that we call theta plus, and then we can draw the negative of that called theta minus. And if we always draw a sample like this, we can end up with the same expectation, because both of them are random samples from the same distribution. And what we will do is we draw pairs of policies like this, and then we get a pairs of rollout from the environment. Let's call them tau plus and tau minus. And then if we write down the policy gradient of this estimate, then what we would end up is basically finite difference with random direction. So here's what it would look like. So basically, we are just plugging in the equation, the policy gradient equation here from last slide. And then if you do a little bit of algebraic manipulation, what you will end up is the following form. So you basically look at what is the positive, what's the return that you get if you take a positive step, and what's the return that, minus the return that you get from a negative step, and then divided by the 2 sigma of it. And this is really closely related to finite difference, and you will see it if I show the equation for finite difference. So finite difference basically looks like the following. For a certain dimension j, you try to perturb it in the positive direction, and then evaluate its output. And then you try to perturb it in the negative direction, and then evaluate its output, and divide it by 2 epsilon. And that's the finite difference. So this is essentially doing finite difference, but you're not doing it in the per coordinate way. What you're doing is you're sampling a random direction, and then step into that random direction. And this is also called simultaneous perturbation and stochastic approximation. Yes?
With reference to this method overall, it seems to be working great for certain problems. I was just wondering if, say, for more difficult problems, you can start with this approach, get some initial value of the theta, and then use the normal approach. Do you guys do it this way, or?
So there are many hybrids that could work well. So I'm not going to talk about them, but there are some recent papers from both OpenAI and DeepMind that are basically trying to exploit some of that, basically combining some of the parameter exploration and the kind of action space exploration. We can talk more about that offline. Okay, so any more questions about this? Yes.
What's the distribution of S1?
It's a standard normal distribution. So then that's why you could reparameterize our current theta distribution in this form. You just shift it by mean and then scale by sigma. Any questions about this? So this all looks pretty simple, but if you just apply them, chances are they won't work. And there are like a lot of practical tricks that you need to get them working. The first type of trick is usually we have some return of certain trajectory, but you oftentimes want to transform the return that you get to be robust against scaling, because like each environment could give you a very different scaling of reward. And 2 of the very common kinds of loss transformation that you would use is you would transform the return of tau into the percentile of tau. And the other also very popular way to do it is you can just set, it's just use an indicator for the best k% of the trajectories. And you realize this is basically a cross-entropy method. You ignore the rest of the k%, and then just do 1 step on the log likelihood of those actions, which is cross-entropy, but this is only 1 step of it. And then the second important part is because we are doing exploration in parameter space, the parameterization matters a lot. So this is what it means. Imagine you're sampling a bunch of Gaussian noise in the parameter space. If all the samples that you get result in exactly the same policy, then you basically have no learning signal, because all of the points would have exactly the same return. So basically, you want to find a parameterization such that it's sensitive to parameter perturbation. So after you perturb the parameter a little bit, it does change. It changes its action that it would take under many different states. So it actually explores different states, different parts of the state space, and then end up with different return. So Rocky and I have looked at using evolutionary methods for continuous control problem with deep networks in in last year, and we actually found that it didn't work really well. So for many, so for the usual kind of multi-layer perceptron that would work well with policy gradient, they usually fail pretty miserably if you just blindly apply the kind of evolutionary strategies that we have mentioned. But a lot of the normalization techniques in deep learning literature can fix this problem. And specifically, there is a method called virtual batch norm, which is basically batch norm. But instead of computing the batch statistics on the current batch, you have a holdout reference batch. And you always compute the mean and standard deviation on that reference batch. And just using these simple techniques can enable evolution strategies to work really well on modern deep reinforcement learning tasks and achieve competitive performance on them. And there are some other tricks that would also help you increase the sensitivity of the parameter space, like discretizing the continuous action space into a bunch of discrete beans, which is kind of analogous to what you have seen yesterday from last Frontiers lecture about how you learn the distribution of values. Also is discretizing the otherwise continuous Q values. And also there are other more novel architectures that would also help alleviate this problem, like DenseNet that was proposed last year. Yes?
So today, John was saying that you recommended you're going to do normalization of your rewards to keep that consistent with the running average over all the episodes.
Yeah.
Here it looks like, if I'm reading this right, that you're doing it per
batch of rollouts. Yeah.
Why one works well, or one would be suggested for traditional RL and one works well for evolution?
So you can also do advantage standardization here. On some problems, it worked approximately as well, but it just seems like percentile kind of transformation works slightly better for evolution. It's just empirical insights. It's not. I don't have like more principled answer for that. Yeah. Right. So I should repeat the question. The question is, what we have seen here is how do we get a gradient estimate? But those are stochastic gradient estimates. Then in deep learning literature, there are a lot of optimization techniques that would help you better optimize your network with this kind of stochastic first order gradients. So the answer is yes. So in fact, in a lot of the, in the next slide, in practice, we do use like Adam. So we would form a gradient estimates with the equation that in the last slide, and then we would feed that gradient into Adam. So it's doing some kind of approximate second order optimization. Yes. Right. So the question is, there's nothing specific to Gaussian here, and in principle, like any other parameter distribution could work. So the answer is yes. So say, but oftentimes it's not that different from Gaussian. So some of the things that we have tried is like Q Gaussian, where you can control the curve of the Gaussian, or something like Cauchy distribution, which has much longer tail. And the truth is, it doesn't make that much of a difference. But you could try even more exotic things. Yes?
Do you sample from or look at non-diagonalized suggestions?
Yeah, so in fact, this is what I gloss over this because, so in fact, like cross-entropy is where we only keep the diagonal. And CMA-ES, which is the method that I said was popular in graphics community, they do estimate the covariance matrix. So which is why they call covariance matrix adaptation. That's where the name comes from. And at least in my experience, it doesn't make that much of a difference.
But you said parameterization matter.
But this is, yes, parameterization matter, but parameterization is about how you go from theta to the function that it represents. But here is more of like you already have some kind of fixed data space and just how you explore it. And then the diagonal Gaussian is just a way of sampling that. Yep.
Does CM like a merge
Yeah, so I guess this is a good question because like you see the loss transformation that we use here is kind of per batch based. So you're kind of optimizing a different reward function at every time step. So the answer to that is I haven't seen it collapse really. So like after a while it just converged to a certain point where like all the solutions are equally good and it basically doesn't do anything there. There was another question.
Methods for making it work in a high-dimensional case.
Right.
Related to
right. So, so the question is, what makes evolution methods work on high-dimensional setting? And the answer is really simple. It's just it's really just to make your parameterization a little bit more sensitive. And in fact, like we'll see a couple examples in the next slide. But basically, like it works basically equally well on all of those Majorco tasks and Atari. If you just normalize a little bit, like even though the network has many parameters, it seems like just doing random exploration would be enough if you normalize your network properly. Yeah.
Other evolutionary programming
right.
They don't always fix the problem.
Right, they don't. So the question is, in some evolutionary methods, they don't take their best k%. So like I said here, like there are many different ways to transform your loss to make it more robust. And say if you do percentile, then it's not just taking the best k%.
Well, sometimes they also they only promote a winner
Right, right. So the question is like in a lot of those genetic algorithms, you oftentimes only promote the winners stochastically. And I would say like what I have presented here is a parametric version of those kind of genetic algorithms where you don't have an explicit meaning of winners. And what's happening is you just move the mean of your parameters slightly closer to the winning to the winners. So in a sense, it's doing that kind of stochastic steps, but in a parametric way. Yes.
Some kind of a measure of how much parameter space is
right. So yeah. So the question is, can you measure how much of the parameter space explore, or do you actually get stuck on local optimal? The answer is you basically always only get stuck on a local optimal. This is a good segue into my next slide. So this type of evolutionary methods can be used to optimize high-dimensional complex control problems like controlling a humanoid. So this policy have, I think, roughly 200K free parameters to tune. And it's learned by, evolutionary methods. And you can basically achieve the same performance as policy gradient-based methods. And one of the crucial differences is that what's shown here is 4 random runs from exactly the same setting, but just with different random seeds. And this is after they have converged. So they have converged onto really different solutions. Like the ways that they work are really different. So to answer the question of whether they explore the whole parameter space, no, they kind of just get stuck on whatever that they found. And what's really funny is if you train humanoid with policy gradient, you usually only discover very similar looking gates. But here, it seems like if you do the exploration in parameter space, you do have a kind of structural exploration that would land you into very different parameter basin that correspond to policy that looks structurally quite different. Yes? Well, they do. Yeah, so that's when you didn't tune your DeepRL method well, they would get stuck in local optima as well. Yes.
How different the rewards are in each of these are they significantly different?
They are about like 10% difference, so not very significant, but they never got better once they get stuck there. Yes.
John, have you compared this to just a pure random search of like uniform weights between -1 and 1?
Right. So the question is, did we compare this with purely random search? We did, and it basically didn't work. Okay. So you do take a while to get off. Like you do need to, it does take a while to find a good parameter space. Yes. My guess is no, but I think like if you continue to train on them with policy gradient, it might find other types of improvement. But in a lot of the policies that we train here, they are actually trained with deterministic policy. So it's actually not obvious how you can switch on like a policy gradient at action level because there's no action noise at all. Yes. Right. Actually, we will talk about that. Yes.
So, like in that, I think this is a generic definition.
Right. Yeah, there's nothing related to RL at all.
Any successful research in other areas where it work well?
Right. So.
What about one of these settings where it doesn't work well? If you look a little bit beyond the RL.
Right. So the question is, like, what are the other areas that you would find this kind of black box optimizers working well? And I think the answer to that is basically everywhere. So if you look in a lot of like other science literature, if they have some simple function that they try to optimize, chances are they're using some black box optimizer to optimize it. And they oftentimes do reasonable jobs. The caveat is you need to give it a reasonable parameterization. Okay. So as I said, this type of method could also be used to learn deep networks that could play Atari games well and learn to discover long-term strategies. And just to summarize a little bit, like what's the kind of advantages of this type of approach? The first one is it works with arbitrary parameterization. So first thing that you can remove is you don't need to have action noise anymore. So there's no real random jittering in your policy. And then the second, even more exotic feature is that now your network could even be non-differentiable. So say your network could be binary. It could have discrete weights, which are a lot more efficient to compute on some devices. And there's no way that you can learn that you can use backprop on those things, except some weird tricks. But for evolutionary methods, it really doesn't care about that. You could have a binary networks, and you could also just learn. Yes.
You're talking about the qualitative differences when you go to Finite walking behavior.
Right.
You watch a lot of videos of EF versus policy gradients on Atari or DeepRL on Atari.
Right.
Can you speak to the qualitative differences in the play and the strategies of those two? I know like around happening and supporting the other guy. Is there like a way to generalize the qualitative?
Right. So the question is for the humanoid robot, we do see qualitative difference in the solutions that are found by evolution strategies and the solutions that are found by action perturbation policy gradient. And then the question is, do we find similar qualitative differences in Atari games? And I don't think so. So I think Atari games are actually pretty simple. You don't actually get to see such diverse play strategies in Atari games. So I don't recall anything that's too significant. But I would say, like, if you have a more complex environment, then I do expect them to emerge different behavior. Then the second thing about evolution strategy is it's embarrassingly easy to parallelize. We'll talk more about that later. And then the cons of evolution strategies is it's not very sample efficient. It's roughly 10 times worse than action space policy gradient. And it's still harder to tune, just because previously people didn't really get this thing to work with deep nets. So the kind of tricks that are needed to make this thing to work are not very widespread or known yet. Yes. We'll touch on that briefly in the end, but I mean, it's basically an open question. I have some thoughts on that, but I don't have a conclusive answer. So next, we would look at why it's embarrassingly easy to parallelize distributed evolution. So to make this concrete, I think it's helpful to just think about what does it take to do distributed deep learning. I guess, first of all, why we care about that. We care about that because in the recent decade, all the deep learning successes are driven by scale. It's basically better data, faster turnaround, better compute, and you get better model. So this is why when we are limited by one worker machine, we really want to scale up and make it train faster. And if we look at distributed deep learning, say it's just supervised learning, what's the most common kind of method that you can use to make your training faster? The most common kind is just do synchronous SGD. So each of your worker look at a batch of data and then calculate one gradient. So all of your workers calculate some gradient, and then you do an all reduce to average all the gradients. And then each worker updates its own parameter. Is this clear, what is happening? Okay. And you can see why this is expensive, because modern neural nets have a lot of weight. And oftentimes you're talking about like each worker needs to send megabytes of data. So this is why it's not very scalable. Like if you go beyond tens of machines, it's just not doable at all. Then let's think about distributed evolution. What needs to be sent in a distributed evolution? So just a recap on the previous slide. We said that it ignores most information about the trajectory, states, actions, reward, so we never send them, which is a nice thing. So if you were to send images, it would also be pretty big. Then the only things that are required by this gradient formula is really just the specific parameter and then the return, as these two terms here. Oops. As these two terms here. So basically what we can think is that each worker sample one parameter data, and then it rolls out that parameter data to get one return. So, okay, so this is one possibility. Each worker communicates its data and the return that's obtained by that data. Is it clear what we are doing here? So each worker will sample its own data, and then it will roll out that data, which might take like 1 minute because it's an expensive simulator, and then gets some return. Okay? So, but we didn't actually solve anything because data is big. Data has the same dimension as your gradient, so we actually didn't solve anything here. But let's say for the case of Gaussian, then we actually know that each data parameter is nothing more than some noise distribution that's like standard normal, but scale and shifted. Okay? So the first thing that we realize is at the beginning of each iteration, the mean is the same for all the workers. So nothing needs to be communicated about this. And then we keep sigma fixed. So the only thing that needs to be communicated is only the specific random noise that you used for each worker. Then the crucial realization is if you do choose epsilon in a completely random way, then yes, you need to transmit the whole random perturbation. But the truth is, in computers, we just use pseudo-random number generator. So what it means is, if I know the seed of the random number generator that you use, I can reconstruct the perturbation that you used. Is that clear? Yes?
Just a continuation. So this is just in simulated environment.
So the question is, are we talking about simulated environment? The answer is it's agnostic to that. So each worker could actually be a physical robot that does something. It doesn't care about that. Because what we are saying here is how you choose the perturbation to your parameter is a deterministic function of the random seed that you use. So if we know the random seed of each worker, then actually we don't need to transmit the whole perturbation. We only need to transmit the random seed in the very beginning. This is a kind of subtle point, but this is like the whole point of this, right?
Why are the mean and standard deviations the same on all workers?
So we are assuming asynchronous optimization. So all the workers perform some work, and then you average all the work together to get a gradient. And then all the worker would take a gradient on mu. So at the beginning of each iteration, they always start with the same mu, which is the same as if you do a synchronized SGD in a distributed supervised learning setting. You always assume you start with the same theta, and then you compute your gradient, you average your gradient, and then you take one step. And then all the workers, again, start with the same theta.
So to start with all the same data, don't they need to communicate since they have to do the all reduced on the gradient? Or?
So right now what I'm claiming here is, this is the gradient. And you can get, you can all reduce the gradient by just knowing these two terms. Right, so each worker, if each worker knows the theta and return of all other workers, they could construct their own gradient. That's synchronized, right? And then what I'm saying is transmitting theta has the same cost as transmitting the gradient. But what we can do is we don't actually need to transmit theta at all. We can just transmit the seed of the random noise that was used to construct theta. Yes? Right, so good question. So now, does it mean each worker needs to recompute the random perturbation, like running the random number generator for a while to get the same vector? Oh, this is a very good question. So on the surface, it seems like this is like trading off between transmission and computation. But in practice, what we do is we can pre-compute a huge table of random numbers. And then all the worker would pre-compute this huge number of random numbers. And then all you transmit is the index into this random number table. So there's no extra computation cost, with the expense of a little bit bias, but that's negligible.
That will require memory as well. So each worker needs to have that much amount of memory.
Yes, each worker has a chunk of memory, but you don't actually need to be that big. Yeah. Yes? Like, we use about 1 gigabyte, and that's enough. I mean, we never tried something smaller, so maybe something smaller would also work. The parameter here, I think, is about, couple hundred K, I think. Couple hundred kilobytes. Yeah, something like that. Okay. So that's basically the algorithms. So each worker could perform some random rollout, and then all you need to send is the return that you get from those rollouts. And you don't need, look at here, it doesn't need to send the specific random perturbation that it has applied to a parameter. And then on each worker, after it has received the return of each specific perturbation, it reconstructs that perturbation on its own without transmitting it. And this is made possible if in the beginning you just pre-synchronize the random seeds among all the workers. So now, if we look at it pictorially, what it means is that we no longer need to send giant vectors. All we need to send are just like small scalars that describe the return of each parameter setting. And this is a lot more scalable. So this is just a demonstration of that. So the task here is the 3D humanoid. And then we are measuring the time that you need to reach a certain return on that 3D humanoid task with evolution strategy. So essentially, if you only use one machine, it takes about 11 hours to solve that task. And if you distribute that onto about 100 machines, you can solve the same task with just 10 minutes. And this is through not specialized networks. This is just machines on AWS. They are not even in the same placement group. So it really have very minimal networking requirement. And this is pretty, this would be really helpful in just the kind of development cycle of, say, new algorithms, new policies, and things like that. Because previously, when you need to train a humanoid, say with policy gradient method, even if you use the beefy machines, it takes 5+ hours to do it. And if you could do the same thing with just 10 minutes, then you can try a lot more things. And because you can achieve a linear scaling, you're not wasting any compute power. Yes?
It seems that with this random search, there's a very high probability of getting stuck in a vertical
Right. Right.
and that's why you need so many workers. So I'm wondering.
They are. Go ahead.
Have you tried with like simulated annealing or something like that, where there's less probability of getting stuck?
Right. Right. So the question is, it seems like this kind of random search would easily get stuck in some kind of local minima. And the truth is, that's the same for policy gradient as well. It's not.
Oh yeah, because like simulated annealing, have you tried that? Or finding good annealing?
No, we haven't tried. We haven't tried something like simulated annealing. But I think that's slightly orthogonal to what we are saying here. What we are saying here is if we fix the batch size, and then to get to the same level of performance, the structure of the algorithm allows it to be more easily distributed, be trained in a distributed way. Yeah. Yes?
Just out of the blue, what stops us from using this approach even in traditional deep learning kind of?
You could. So, okay, very, very good question. I'll talk about this at the end. So the question is what stops us from using evolution in, say, supervised deep learning? And the last bit that I want to touch on too is you do incur a worse sample efficiency. So what we are comparing is TRPO, the algorithm that we learned yesterday, and evolution strategy, which is in orange. So you will see on most of the tasks, you do suffer about a 10 times performance, 10 times sample efficiency penalty. Meaning to achieve the same level of performance, you usually you need to use 10 times more samples. Yeah.
So the fact that we are doing productivity is because of analyzing.
Right. So the question is, but we can parallelize better. So we can basically solve most tasks in faster world clock time than policy gradient. But it is indeed a trade-off. Say you are learning, if you are trying to apply RL to a physical system, then you don't get to infinitely parallelize it just by adding more machines. But if you are doing it with a simulator, then evolution strategy, it's a very good way to go, especially if you want fast turnaround time. Yep. Yeah, the code is published on GitHub for the distributed version. So you can actually see how we set up the networking on AWS and things like that. Yep.
It seems like we're all the graphs at the moment where the two minds pass each other.
Right.
Have you ever tried using some sort of system where you use this and then switch
to I think that's a good idea. We haven't tried anything like that. Yep.
In all distributed settings, there's always the possibility of workers' failure, weights not getting updated, base conditions. How are those sort of things handled?
So the question is, in like large-scale distributed settings, you would need to deal with worker failings and things like that. So if the worker's failure is a random variable that's independent of the performance of the policy that is sampling, then even if you drop workers, it's basically the same because you're just averaging with fewer samples. Okay, so just kind of summarize and kind of as some food of thought. So yeah, we have this kind of evolution strategy that basically is full episode evaluation. You try one parameter, and then you run it for one episode, and then it gets you a return in the end. And you do parameter perturbation to search in the policy space. What you get is more structural exploration, like you see in humanoid. It explores qualitatively different behavior. And the other benefit of that is this thing is not biased by discount factor. So we have learned the discount factor is helpful in policy gradient at action space to reduce the variance. But that usually is not something that you want to do. Sometimes you oftentimes care about undiscounted return. You want to care about the return at the very end of it, not just in a short-sighted return. And we have also seen this thing is very easy to scale, very easy to get quick turnaround time. Then I guess we should end with an open question. That is, policy gradient at action space. That's what we have seen yesterday. And policy gradient at parameter space. That's evolution, a parametric kind of evolution that we have seen today. Like, which one is better? So one important thing to remember is that fundamentally both are derivative-free optimization. Because when you do policy gradient, what you are effectively doing is you try random things at the action level. And then you try to see which action is better. And then if you do a policy gradient at parameter space, you are trying which parameter is better. But in the end, either at the action part or at the parameter part, you don't get gradient access there. So both of them are fundamentally zero-order optimization problem. Then the question is, when is one, so basically for both spaces, we can do random search. But which one is better? So it seems like if your episode is really, really long, and you need to sample many, many actions, then them adding together might be less efficient than just directly search in parameter space. So say if you have an agent that needs to live for 1,000,000 time steps, maybe per action policy gradient is not so effective in that setting. But this is, again, an open question. There's no conclusive answer there. And maybe it's also true that there's a better action space to be discovered that would allow for more effective search. And that's, I think, a lot of the promise of hierarchical reinforcement learning. Can you learn some kind of action hierarchy that allows you to explore much better than simply parameter space or just straight up action space? And to answer the question of why don't we do this in supervised learning, the answer is when you do have access to a true gradient, it actually makes your optimization a lot easier. So in the literature of stochastic convex optimization, there are minimax bounds for the situation where you have gradient access and the situations that you don't have gradient access. So in minimax sense, that is in the worst possible case, you always suffer a certain factor of slowdown if you don't have gradient access. So that is why in supervised learning, where you do have you do have an approximation of true loss, say cross-entropy, that's when you should always use the gradient as opposed to use evolution. Any other? I can take maybe one more question. Yes. The answer is you always, well, in the minimax sense, you always incur a slowdown by not using the gradient. So if you have access to true gradient, you should always use it. And my point being, policy gradient at action space and policy gradient at parameter space are both zero-order optimization, meaning you don't have access to true gradient in either case. It's just the difference between random search. Versus in supervised deep learning, you do have access to true gradient, and you should use it. So there are some works that try to apply evolution to deep nets. I don't remember the results, but specifically there are some internal efforts at OpenAI that were trying to apply basically evolution to supervised learning, and you do see a large factor of slowdown. That's not easy to mitigate by just distributing more. Yeah.
Yeah, I think you mentioned earlier that you thought it's non-trivial to figure out how to hybridate from evolution back to policy gradient. Can you talk a little bit more about what
It really depends. Also, the question is, why is it hard to have a hybrid of evolution strategy and policy gradient at action level? So it's not hard if you set it up the right way. So if say the policy class in your evolution strategy is a stochastic policy, then it's actually very easy to apply that. And I can also point you to some papers that are trying to do that. Okay, so also happy to answer questions on Piazza. If you have any questions, just post it on there. Thank you, guys.